Hello, this is Mr. McCloy. In this video, I'm going to talk to you about work. You should take notes during the video. Feel free to pause and rewind as we go if you would like to hear or see something again. By the end of the video, you should be able to understand the difference between the way we use work when we're talking to friends or each other, and what specific meaning scientists have when they use the word work. You will also be able to define work by relating it to the concepts of force and displacement. By the end of the video, you should be able to analyze a given situation and identify whether and where work is being done. You should be able to calculate the net work done by one or more forces applied to an object. Now, let's get started on that first objective. When you hear the word work, what do you think of? Pause the video and take a moment to write down what work means to you. Work can mean different things to different people. It can be homework, schoolwork, whatever you get paid to do, or what it is you do that allows you to do what you really want to do. Work can mean working out, or practicing sports, or rehearsing with a musical instrument. It can be cleaning your house, or babysitting, or teaching, or learning. But in physics, in science, work has a very specific meaning. In physics, work is defined as a force being applied over a distance. Remember, a force is a push, or a pull. So, for this definition of work, an object would have to be pushed, or pulled, and it has to move. Now, there's two main points to that definition. The first is that the force needs to have some component in the same direction as the object moves. Think about a student lifting a textbook. Watch the student lift the book. What direction is Oscar applying a force to the book? Oscar pushes up. And in which direction does the book move? The book is also moving up. Now, since Oscar is pushing up on the book and the book is moving up, it's in the same direction. Therefore, Oscar is doing work. What if the force is perpendicular to the movement? Perpendicular forces do not do work. Let's see another video of a student carrying a book across the room. Which direction is Oscar pushing on the book? He's holding up the book. He's making sure that gravity does not push down on the book. So the direction of Oscar's force is up. Now, which direction is the book moving? In this case, Oscar's carrying the book to the left. The force is perpendicular to the direction of motion. Therefore, Oscar is not doing work. The second main point is that the object has to actually move in order to do work. If Oscar is holding the book up, then, yes, his muscles may get tired. He is applying a force. In fact, he's holding the book up. But what about the motion of the book? The book is not moving. Even though Oscar's applying a force, because the book doesn't move, Oscar is not doing work. Let's compare the work of two different people. I had a student come to me, said, "Mr. McCloy, I really need some community service time." I said, "Oh, all right, well, how much time do you need?" He said, "I need an hour. If I don't get an hour, I'm not going to graduate." I said, "Okay, tell you what, I will let you do an hour of community service if in that hour you do more work than I do." He said, "Sure, okay, yeah, I can do that. What are you going to do?" I said, "Oh, me? I'm just going to watch you work." He said, "Oh, easy. I can definitely do more work than that." I said, "Great. Okay. See that wall there? I want you to push against that wall as hard as you can." And so he started pushing against the wall. And he pushed. And he pushed. and he started sweating, and he kept pushing. And I said, hold on, I'm getting a little tired. Let me pull this chair across the room here. And so I pulled the chair across the room, and I had a seat, and I watched him pushing and pushing and pushing. Finally, at the end of the hour, he just collapsed on the floor. He said, oh, Mr. McCloy, that was the hardest hour I've ever had. That was the most work I've ever done. I said, hold on a second. Hold on. You were supposed to do more work than I did. I said, what are you talking about, Mr. McCloy? You were just sitting there. I said, yeah, I was just sitting there, but I still did more work than you. I said, you're crazy. Well, think about it. First of all, who used more force in this situation? There was the student pushing against the wall with all he had for an hour, and then there was me. I didn't do much. I dragged a chair across the room. So, the student definitely used more force. But, who went a greater distance? Now, this student was pushing against the wall, and he was pushing hard. I saw him. I watched. He pushed hard. But the wall didn't go anywhere. He didn't go anywhere. Me, I used a little bit of force to move that chair, and I dragged it all the way across the room. The student didn't move. I went further. Therefore, who's done more work? I'm the only one who did any work. That student didn't do a bit of work according to the definition by physics. Now, because this is physics, of course, we have an equation. If the force is parallel to the movement, the equation for work is W, work, equals the force times the distance that the object moves, F times D. We measure work in something called joules, which we abbreviate with a capital J. And 1 joule is the equivalent of using 1 newton of force while an object moves 1 meter. So 1 joule is 1 newton meter. Take a minute now to update the table at the back of your notebook. The variable for work is W, the quantity is work, and the unit is joules, J. Pause the video and put this into the back of your notebook. Now, that equation applies if the force is parallel to the direction of movement. However, if the force is not parallel to the movement, the equation for work is a little bit different. Work equals the force times the distance times the cosine of theta. And theta is the angle between the direction of movement and the direction of the force. If someone's pushing a crate across the floor, they're probably not pushing exactly horizontally. They're going to be pushing down and across on the crate. So the angle theta is the difference between the direction of the movement, the crate's moving horizontally, and the direction of the force. This equation actually works if the force is parallel to the movement. In that case, theta would be 0. Cosine of theta is 1, so it still works out as work equals force times distance. The last topic is the sign of work. Now, work is a scalar. It's not a vector, it's a scalar. It only has a quantity. But, unlike most of the scalars we've had, it can be positive or it can be negative. Work is positive when cosine of theta is positive. That's going to be if there's less than 90 degrees between the force and the direction of movement. Or you could say if the force is kind of pushing in the same direction as the object is moving. So if you have a d displacement vector, like you see here, and a force vector, as long as it's less than 90 degrees for that theta, that force is going to do positive work. It's negative work if the cosine of theta is negative. That means that the force is basically pushing in the other direction than the movement. If the force is opposite the movement or working against the movement, like so, then your theta is going to be greater than 90 and the work is going to be negative. Okay, that's everything you need to know about work. That's all.